All right, we can now move on to section 4.4, which talks about the mean value theorem. Before we can talk about the mean value theorem, we have this other thing called Rolle's theorem. Let f be continuous over the closed interval from a to b and differentiable over the open interval from a to b, such that f of a is equal to f of b. Then there is at least one c within a to b such that the derivative at that point, just to make this clear, the derivative of that point c is equal to 0. So remember we said when the derivative is equal to 0, that means my curve is flat at that point, right? So this is saying if my two endpoints A and B are at the same y, then somewhere between them it has to be a flat line. So let's think about that. Let's say f of A is right here and f of B is right here. Like I said, same y. So then they are at the same height, okay? Three things might happen. The first thing is I might leave that point and start going up. If I start to go up, we know since these are at the same y that at some point I'm going to have to turn around to come back. Therefore, at this point right here, I have a flat line. So then that's true. There had to have been a point in here so that I have a flat line at that point. Okay. What also might happen is I might go from my first point and then start going down. But again, like we said, it has to somehow come back to this point. So I would have to turn around and come back. In which case, right here, I had to have had a flat line at this point. So that's true. Another thing that might happen, start here, end up there, I could just stay straight. In which case, if I'm just a straight line, then obviously it's a flat line over the whole thing. So that's why that is true. If they end up, or if they start and end at the same point, no matter what happens between them, it could be a bunch of things, right? Somewhere along there, at least one point, there had to have been a flat line somewhere. And I can see right here that's clearly true because if I leave from this point, I have to somehow come back. So I will always have a flat line somewhere between them. Let's look at a few examples examining that. Example. For each of the following, verify that it satisfies the conditions of Rolle's theorem and find all the values of C such that f prime of C is equal to 0. The first one we are going to do is f of x equals x squared plus 2x. So what I want to make sure first is that it satisfies what says must be true in order to do this, okay? It says f has to be continuous from A to B, including those. So if I look at my first one, part A, I can see this is continuous because there are no restrictions on what the domain can be. So this is obviously continuous, again, because there are no restrictions over the interval -2 to 0. And I can tell that it is differentiable, which is another condition. Differentiable from A to B, because I can take the derivative and plug in anything I want to. So, the differentiable over the interval -2 to 0. So that first part here, we are good. So now I have to also check and make sure f of A is equal to f of B. So f of -2, let's start there. That would be -2 squared plus 2 times negative 2. Negative 2 squared is 4. 2 times the negative 2 is negative 4. So that gives us 0. Now I should be able to plug in 0 and get this the same thing. So that'd be 0 squared plus 2 times 0. Look at that, we get the same thing. So since every condition is true, I can use this. Okay? Since everything is true on the if part, then I'm good. So now I know there is a point between them such that the derivative is equal to 0. So they want us to find where that is. So first, let's find what the derivative is. F of x is equal to, for x squared, bring the 2 down, make it 2x. 2x becomes 2. And I want to set that equal to 0. Solve that. We just subtract 2. 2x equals negative 2. Divide by 2. X is equal to negative 1. Which, if I look at that, is between them. So that is good. So C is equal to negative 1. Negative 1 is a point between negative 2 and 0. And the derivative at that point is equal to negative 1. Let's look at another example of doing the same kind of thing. This time we're going to do the same thing, except f of x is going to be equal to x to the third minus 4x. So again, the first thing I need to check and make sure is that f is continuous and differentiable. Well, there are no domain restrictions, so that's good. So I am continuous. That's good. And I can take the derivative and plug in whatever I want to for x. So it is also differentiable. That part is good. So now I just need to make sure that f of a is equal to f of b. So plug in negative 2. Negative 2 cubed minus 4 times negative 2. Negative 2 cubed is negative 8. Negative 4 times negative 2 is positive 8, so 0. Do the same thing for 2 and make sure they're the same thing. 2 cubed minus 4 times 2. 2 cubed is 8. Negative 4 times 2 is negative 8. So I get the same thing. So that is good. So since f of a is equal to f of b, I can use this. And that's fine. So I know there is a point between them such that the derivative is equal to 0. Let's find it. So first take the derivative. X to the third, bring the 3 down, and that becomes 3x squared. Negative 4x becomes negative 4. Set that equal to 0. Add 4. 3x squared equals 4. Divide by 3. X squared equals 4 thirds. Take the square root of that. X is going to be equal to plus or minus the square root of 4 over 3. Let's see if I can like this. The square root of 4 is 2. So that's 2 over square root of 3. 3 is not a perfect square, so that would have to stay square root of 3. But remember, we do not like having square roots in the denominator. So to get rid of it, multiply by the square root of 3 over the square root of 3. So plus or minus 2 square roots of 3 over square root of 3 times the square root of 3 is 30. So it happens at 2 square roots of 3 over 3 and also at negative 2 square roots of 3 over 3. So this one actually had 2 points. All right, from Rolle's theorem, we have another theorem called the Mean Value Theorem. Let f be continuous over the closed interval from a to b and differentiable over the open interval from a to b. But that's all that it says must be true about f, right? On the last one, it also said f of a has to be the same as f of b, right? It does not say that here. So the only thing I've got to check and make sure is that it is continuous and differentiable. If that's true, then there exists at least one point C between A and B where the derivative at C is equal to f of B minus f of A over B minus A. Notice what this is. This is the slope, right? This is the slope between point A and point B. So remember also the derivative is the slope at that point. So what this is trying to say is if I have a point right here and a point right here, and I'm doing something between them, it doesn't really matter what it is. Somewhere on that graph, the slope of the tangent line is going to be the same as the slope of the line between A and B. So looking at this line, somewhere on here, the slope of the tangent line is going to be the same as the slope of that line. So I can actually see that happens about like right here. The slope is the same right here at this point. So that's what this is trying to say here. If I can go from A to B, there is somewhere on this curve where the slope of the tangent line on that curve is the same as the slope of the line between A and B. We can actually apply this to speed, and that's really nice, okay? If I know what my average speed is, I know that somewhere while I was on my trip, I had to have gone that average speed, right? So somewhere on there, I had to have gone that speed, right? So like if I'm going on a trip and I say that my average speed of that trip is, let's just say 45, okay? Then somewhere along the line, somewhere on my trip, I must have gone this speed. That's basically what that says. And that's very cool. All right, let's do an example of using the mean value theorem. Example, for f of x equals the square root of x from 0 to 9, show that f satisfies the conditions of the mean value theorem. Then find the values of c such that the derivative at c is equal to f of b minus f of a over b minus a. So remember, the only thing I need for this one is that it is continuous and differentiable. Okay. Well, the only domain restriction I have on the square root of x is that x has to be greater than or equal to 0 because it's the square root, right? Well, since that's where my domain is going to start, then that's fine. So it is continuous, again, because the restriction does not apply to the part of it that I want right here. And then I can take the derivative of that and plug in anything inside of here, right? So that is also differentiable. So we're good. So I know there has to be a point between 0 and 9 such that the derivative at that point is equal to the slope of the line from 0 to 9. So first, why don't we find what that slope is? So f of b means the square root of 9 minus f of a, so that's the square root of 0, over b, which is 9, minus a, which is 0. Let's work that out. Square root of 9 is 3, minus square root of 0 is 0, over 9 minus 0 is 9. On top we get 3 over 9, which is like saying 1/3. So the slope of the line between those 2 points is 1 over 3, right? So I want to find where is the derivative equal to that. So let's find the derivative of f of x. The derivative of the square root of x, we have said this a bunch of times, is 1 over 2 square roots of x. So I want to know where that is equal to 1 over 3. Well, on top I can see I have 1 is equal to 1. So what I must have is 2 square roots of x be equal to 3. I can solve that by dividing by 2. Square root of x equals 3 over 2. I have a square root, so square it. Square both. 2 squared is 4. So at x equals 9 over 4, the derivative at that point is the same as the slope of the straight line between x equals 0 and x is equal to 9. Those are going to be the same. Using these two theorems, we can come up with a bunch of extra facts that we are going to use in this class. Okay, I have them all right here. The first one, let f be differentiable over an interval I if the derivative is equal to 0 for everything inside of that I, then f of x has to be a constant. Okay, so what this means is if the derivative is equal to 0 for every value of x, then it must be a constant. Let's think about that, okay? If the derivative is equal to 0, that means at that point I have a flat line, right? Well, if I have a flat line for everything, this means my graph is just going to look like this. It's just a flat line forever and ever and ever. Well, that happens when it's a constant. So that makes sense there. The next one, if f and g are differentiable over I, and the derivative of f is equal to the derivative of g, then f of x must be the same as g of x plus some constant c. This one might not be as clear at first, but if we think about this, remember that the derivative of x squared is equal to 2x, right? But think about what the derivative of x squared plus 9 is, right? Well, from the x squared part, I get 2x, and then I know that the derivative of 9 is equal to 0, right? So it's just 2x. So the derivative of x squared is the same as the derivative of x squared plus 9. So what this means is when the derivatives are the same, then what I started with are the same thing, except I can add a constant, because that constant is not going to change my derivative. That's what this means. We are going to use this a lot in section 410, and then as well as a lot in chapter 5. And for those of you who go on and take Calc 2, we are going to use this fact a lot. This is very helpful. And then my third one, if f is continuous from a to b and differentiable, then if the derivative is positive, f of x is increasing. So remember, the derivative is my slope. So if my slope is positive, that means my graph is going upwards. On the same note, if the derivative is negative, it must be decreasing. Again, because this is my slope. So if my slope is negative, then it is decreasing. All of this stuff is going to help us draw graphs in the rest of chapter 4.